the influence of the mass and stiffness of elements of mechanical systems on the characteristics of their vibrations. Article 11.2 from the book Mechanical Systems Calculations of the Marine Facilities. Okay, let's consider the system of suspended load suspended by two springs connected in series. The first spring with the stiffness characteristic of C1, stiffness is the force which arises when this spring has the deformation per the unit of the displacement. And the second connected in series spring is of the stiffness index C2, and this is indicated on the right, the forces acting upward, the forces of the elasticity of the deformed springs F1 and F2, and we have as well the load, the material point, so concentrated load if we neglect the sizes of this load. And for this considered system, indicated on the figure 11.2.1, we have to decide that the force of deformation of two springs connected in series is equal to the force in one spring and the second one, and the first and then the second, due to the springs are connected in series. And the force which arises in the first spring is equal to product of elasticity index of the first spring by the deformation of first spring. Exactly for the second spring, the force of elasticity equal to multiplication of the stiffness characteristic of second spring by deformation of second one. And let's substitute this system of series connection of two springs by the another scheme on the figure 11.2.1b with only one spring, equivalent spring, which characteristics of stiffness and characteristics of elasticity will be the same as the common characteristic of stiffness of two springs connected in series. So the force of the elasticity action on the load for this equivalent spring equal to the product of the stiffness characteristic of this equivalent spring equivalent to the previous one multiplied by the deformation of this spring, this formation of spring equal to the displacement of the load, the material point of the concentrated load with the mass m. And the deformation equal just as the total of the deformations of the springs C1 and C2. And we have the deformation of the equivalent spring. If we substitute instead of the deformations in this last equation, the deformations got from the previous equation. So as delta 1 equal to the fraction F1 divided by C1, the deformation delta 2 equal F2 divided by C2, and the deformation delta equal to of the equivalent spring equal to the force elasticity divided by C, and we will have in the account that the forces of the elasticity equal to the weight of the load. So we have the same load in both cases. So the forces of the elasticity equal F equal to F1 and F2. And after the substitute, after the cancel of the common factors from the resulting equation, we will have that the relation between the relation besides among the factors of the elasticity of the equivalent spring, C elasticity characteristic or stiffness characteristic, and the elasticities of the two original springs connected in series would be in the indicated relation, indicated relation. And after mathematical transform, we can find that when we have the connection of springs in series, the equivalent stiffness will be the fraction. In the numerator we have product of stiffness of the assigned originally connected in series two springs, and in the denominator we have the total of the stiffnesses of these springs. As well, if we have not two but more springs connected in series, we will have more factors in the numerator, and we have more summands in the denominator as well. So this is as more springs we have connected in series, so softer will be the equivalent spring. This suspension as equivalent to the considered one have to be more softer due to the common stiffness of many springs connected in series reduces accordingly. So let's consider the options of the connection of springs to the unit load. Now, on the figure 11.2.2a is shown the parallel connection of springs. So for the parallel connection of springs, not the connection in series, but parallel connection of two springs, the common stiffness of the springs, if we assume the suspension for the equivalent spring with the same stiffness as the 2-1, have to be the equivalent stiffness, like indicated on the figure 11.2.2c. The equivalent stiffness will be equal just to algebraic total C1 plus C2. And let's consider the suspension as shown on the figure 11.2.2b. This looks like a connection of springs in series, but the important difference is that this both two springs connected to the support, because in the sample we considered before on the figure 11.2.1, we have two springs in series connected second to the first one and the first one to the support. Here we have two springs connected to the supports. So this scheme of the connection of springs to the load and to the support equivalent to considered option 11.2.2a when we have the parallel connection of two springs. So here, as well as here, in the option B, the same as in the option A, we have the equivalent stiffness of two springs connected parallel here. This we have to consider as a parallel too, just due to the displacement of the load to any direction. One spring will compress, another one stretched. In both cases, the restored force dependent on the deformation of spring will restore the load to the initial position, and the springs will do like in parallel. So two stiffnesses acts as the components of total for the equivalent spring. And let's consider exercise. Exercise 1, we have the load suspended by the spring of the stiffness C, stiffness index C, or the load of the mass M. And let's consider what if we have the two springs connected in series to the same mass. What we can say about the cyclic frequency of the oscillation of this load. Cyclic frequency depends on the stiffness characteristics of springs and on the mass of the suspended load. As these two springs connected in series, we have that C2 is the equivalent stiffness if we substitute these two springs by the only one spring, unit one, for the suspension of the load of the same mass. The stiffness of the equivalent spring, which can be substitute of the indicated two springs connected in series, will be like a like in the relation indicated here in the formula. So the fraction 1 divided by C2, the stiffness of the equivalent spring, equal to 2 equal springs. We can see that both springs are of the same stiffness characteristic C. So as we will substitute these two into unit, we will have that after mathematical transform, that the stiffness of the equivalent spring instead of these two springs will be the C divided by 2. C is stiffness of each one spring connected in series. How it impacts on the cyclic velocity of the oscillation of the load suspended on the springs connected in series. So we know that the cyclic velocity equal to square root of the fraction of the stiffness index divided by the mass of the suspended load. And if the stiffness after by the parallel by the connection of the springs in series reduces twice, so the suspension became softer. So when we substitute this to the formula of the determination of cyclic frequency, we can find that the cyclic velocity reduces under root. We have the factor 2 in the denominator, so reduces at about 1.41 times, 1.41 like that. And the integration constant in the formula, we have the formula of the type of the decision of the second order linear homogeneous equation of free oscillations of suspended load. And we have to find the constants to have the decision, and these constants as well. This constant enters into the mathematical equation to find the amplitude of the oscillation. And if we adopt the initial conditions for the time period equal to 0, for the time moment equal to 0, that for the suspension only by one spring and for the suspension by two springs in series, the initial displacement of the load equal to 0 and the initial velocity equal to v0 for the both two options A and B of the suspension of the load M by one spring and O by two springs in series. The initial velocity will be equal to v0 at the same time period. Then we can use the formulas to determine of the amplitude of the oscillation of the suspended load in the initial case when the load suspended by one spring, and in the assigned case when the load suspended by two springs in series. In this case, we would be able to find the change of the oscillation's amplitude independence on the double suspension in series by the same springs. So if we keep deciding this equation, and we can find that amplitude of the oscillation in the first case when we have the only one spring of the suspension of the stiffness index C. So this impacts on the cyclic velocity K. It enters in the equation for determination of the amplitude of the oscillations in the suspension only by one spring. Here is equal to the summons one squared summand is equal to x0, another one summand under the root for finding the amplitude equal to V0 divided by K squared. So if we will have, for the first case, the characteristics of stiffness of the spring and the characteristic of the mass of the load, like indicated here in the formula, we will have the amplitude, assuming that the initial displacement of load equal to 0, will have the amplitude of the oscillations, like V0 multiplied by square root of the fraction of the mass of the load divided by the stiffness index of the spring. If we connect it to springs in series, that is in the denominator under the root here, we have that the stiffness characteristic of the spring is C divided by 2 in the denominator of the denominator, so squared as well, everywhere we have squared, because this is Pythagorean theorem. And we will have that the amplitude in the suspension, for the case of the suspension of the load by two springs in series, will be as the previous one, V0 by multiplied by square root of the m divided by c, but multiplied by square root of 2. Square root of 2 is about 1.41. So when we suspend these two springs in series, the amplitude of the oscillation increases in the proportion of square root of 2. This is due to the consequent connection in series of two springs of the same stiffness characteristic. If under equal conditions to introduce a second spring of the same stiffness connected in series with the first one, the ratio of the amplitudes of oscillations of the material point equals A2 divided by A1 equal to square root of 2. This is about the same, but it's more for square root of 2. And the cyclic or circular velocity, if we suspend the second one load to this with the same mass to this springs connected in series, what will be the amplitude and the frequency cyclic velocity of oscillation. The frequency of oscillations will also decrease by square root of 2 times of the second load if the second load of specified mass is suspended at two springs connected in series, like indicated in the like shown in the figure 11.2.3c. So when suspending one load of the mass m, the cyclic frequency of free oscillations will be, so this is for two springs in series, we suspend one load of the mass m. And if we have the in third case, we have two loads suspended, 2 by m, total m of two loads equal 2 by m multiplication. So the NC2 is equal as C divided by 2. So this is the suspension of two springs in series, two same springs. So the stiffness reduces twice. In this case, after the suspension to two springs in series of the second load, the cyclic frequency reduces not for the square root of 2, but for 2. So on first time, we have the cyclic load, which compared to the original one, suspension for just only one spring. For two springs use of one load, the cyclic frequency reduces by 2 square root in the denominator. But if we apply the second one load, this will be not K2, but K3. K3 is the cyclic velocity of the oscillation of two loads on two springs in series. So this second load reduces for more square root of 2 times than the suspended one load to two springs in series, which use B less for square root on in the first case, less for square root of 2 times. So the frequency of the oscillation, I mean the cyclic frequency, will be less for 2 times. If we suspend 2 loads of same mass to 2 springs in series of the same stiffness characteristics. Okay, let's consider another one exercise. Exercise 3. We have 2 springs, 2 loads of the masses M1 and M2 suspended to the springs of stiffness characteristics C1 and C3. In the option first, the spring stiffness is equal, C1 equal to C, and the stiffness C3 equal C divided by 2. And the mass in the first option here is of the load equal to just the mass M, and the mass in the option 3 here of spring stiffness is equal C divided by 2. C is equal to the stiffness C1. And the mass of the load will be twice more than M2Ms. The typical frequency of re-oscillations in option 1 is K1 equal to square root of the fraction stiffness characteristic C divided by the M, mass of the first load equal to M. And the option of 3, the cyclic frequency is equal. We have twice less stiffness characteristic in option 3, and we have twice bigger load for this all in the denominator under the root. So the cyclic frequency in the option 3 equal to timeless twice, just a half of cyclic frequency of the load oscillation in the first option on figure 11.2.4a. In option 1, the load of the specified mass suspension on the spring of stiffness C1 equal to C, the amplitude of the vibration will be just because we assume that the amplitude of vibration depends on the initial conditions. This is obviously that the amplitude of free oscillations of load depends on the initial conditions, and we assume that the time moment of time equal to 0, the initial time moment, the amplitude of the vibrations depends on the initial velocity, but it depends on the initial velocity divided by k. K is the frequency of the velocity, or we can multiply by the factor square root of m divided by c, just because this is equal to 1 divided by k, cyclic velocity. And for the case 3, the amplitude of the vibration as well, we have we assume that the initial displacement of the load in all cases equal to 0. So due to the determination using the Pythagorean theorem, we assume the second sum, and the second sum depends on the initial velocity. And if we consider for the case 3 that the mass is equal twice in the mass in the first option, and that the stiffness characteristic of the spring will be twice less. So this all we introduce in the equation here, and we will have that the amplitude of the oscillation of in the case 3 with the softer spring of the smaller we have the stiffness characteristic of more softer spring. Stiffness characteristic of spring is twice less in the mass more heavy system in the case 3. Twice mass of the suspended load more than in the case 1. So the amplitude, the proportion between the amplitude of the oscillation for the same initial conditions of zero displacement at the initial moment of the load, and for the same velocities of the loads at the initial condition, but the amplitude of the oscillations in the option 3 will be amplitude twice bigger than in the option 1. And let's consider exercise 3. Let's consider on the figure 11.2.4b the load of mass M suspended by 3 springs, and each spring connected to the load, at the same time connected to the support. So this actually is not the connection of springs in series, but this connection of springs in parallel. The load of the mass 1 kilo is suspended to 3 springs with the stiffness coefficient of the first spring 2 Newton per centimeter. So the stiffness characteristic of the spring is force rising in the spring when we deform the spring for just 1 unit of the deformation. If you consider centimeter could be Newton in the international system of the units of the force, centimeter we next can transform to the dimension of Newton per meter. So, and we have 2 other springs here on the scheme is below C2 and C3. The stiffness is equal to 7 Newton per centimeter, and they are equal to. So we first have to find the common stiffness of all springs acted in the parallel. Acting in parallel, we have that this is 16 Newton per centimeter. That is the stiffness of all springs together acting on the load is 16 by 10 squared Newton by meter. The cyclic frequency equals, we can substitute instead of the M mass of the 1 kilo, and instead of stiffness 16 by 10 squared, and we will have 40 seconds in the degree minus 1, power 2 minus 1 of, this is cyclic velocity, cyclic frequency that is in radian per second. So if we will have the technique frequency, so frequency of harmonic oscillations, the number of oscillations period per unit of time. So we can use the cyclic frequency and the frequency of harmonic oscillation. We will divide this by 2p. 2p is, and we will have the frequency in the amount of the oscillations. This is the unit of the Hertz. Hertz is not the radian per second like we have here. And for the cyclic frequency, the dimension is radian per second. We indicate radian just as unit of the angle, and per second mean that second in the denominator, that is second in power by minus 1. And this is the number of the cyclic periods of the oscillation per unit of time. This is Hertz unit, period of harmonic oscillations per second. Questions and comments. Mechanical system rigidity by serial and the parallel connection of springs. When we connect springs by serial, so the stiffness characteristic increases of the connection. I mean the elasticity increases. The rigidity characteristic and of serial connection of springs reduces in the proportion. In the numerator we have the product of stiffnesses of 2 springs connected in series, and the denominator we have total of the stiffnesses. Actually, we reduce the stiffness of total suspension for the parallel connections of springs. The stiffness increases, and the stiffness of the parallel connection of springs equal to the total of the stiffnesses of all springs connected in parallel. 11.2.2, the influence of additional mass, the mass doubling attached to the concentrated load on the cyclic frequency and on period of the oscillations, as well as on the amplitude of the material point oscillations. The impact of the additional mass increases the amplitude of the oscillation, increases the softness is about the same as the increase of the softness of the suspension, as a reduce of the stiffness of the suspension in the same proportion, like we have in the parallel connection in the connection in series of two springs connected in series. This gives us the increase of softness of suspension and reduce of the stiffness of the suspension. So, and if we attach instead of one load, two loads to the spring, two loads, so the stiffness, so the cyclic frequency reduces for the same two loads equal suspension. The cyclic frequency reduces by the factor of square root of 2 is about reduces in 1.41 times. And the amplitude of the oscillation increases for the same proportion in square root of 2 times after the suspension of two loads instead of one for the same spring. 11.2.3. The influence of an attached spring of same stiffness on a cyclic frequency period and amplitude oscillations. If we attach spring of the same stiffness, it depends on what is the scheme of the attachment of springs. If it is attached, the springs attached in series, so the stiffness reduces. If we have the same springs, reduces in proportion of how many square root of in the proportion of dependence on how many springs we attached in series. If we attach springs in parallel, so the stiffness, common stiffness of all suspension equal to total of the stiffnesses of all springs in the suspension. The cyclic frequency for the connection of the springs in series reduces in the proportion of the square root of reduce the stiffness of the suspension by the springs in series. The period accordingly, period of the oscillation increases and amplitude of the oscillations increases for the same proportion as square root of the proportion of the stiffnesses of suspension of the springs in series in accordance with the suspension to just only one spring maybe of the bigger stiffness and the lesser softness than the springs in the series. Exactly the oscillation increase in the same proportion, but if we suspend to the springs connected in parallel, so the frequency increases in the stiffness of the total suspension equal to the total of stiffnesses of the springs in the parallel suspension. The frequency increases in the proportion of the square root of the increase of stiffness of the parallel suspension of springs. The period of the oscillation reduces in the same proportion as the stiffness of the suspension of the parallel connection of springs is bigger than the stiffness of just only one spring. We consider the square root proportion. And the amplitude of the oscillation of the suspension by the springs in series reduces in proportion of the square root of how much stiffness of the suspension of few or a definite number of the springs connected in parallel. The 2 by pi ratio of harmonic oscillation frequency and the cyclic of the circular frequency. We can consider two frequencies. One frequency is which is the how per unit of time how many the oscillations we have of the load suspended by spring. This is the frequency of the harmonic oscillations, and the unit is Hertz. Hertz is the number of oscillations per unit of time. Unit of time, the Hertz usually used in the International System of Dimensions, and the Hertz is how many oscillations per second. And the cyclic frequency is proportional to frequency of the harmonic oscillations, the frequency of harmonic oscillations, or so-called technical frequency, number of the oscillations per unit of time. But the cyclic frequency is number of the radians of the period of the oscillation per unit of time. As cyclic frequency, they are in the proportion of 2 pi between the frequency of the harmonic oscillation is equal to cyclic frequency divided by 2 pi. And the period of the oscillation as well is equal to just 1 divided by frequency of harmonic oscillation, or the period oscillation is equal to 2 pi divided by cyclic frequency. This is period of the oscillations. Thank you.